Okay, yes, we have some rules of integration we're going to go over here. Okay, so I'll start with just a function. F of x equals x to the n. The derivative of that is n times x to the n minus 1. Bring your exponent down, multiply it, reduce the exponent by 1. The derivative of that, or so the antiderivative of that, would be increase your exponent by 1, divide by the increased exponent, plus c. Now, some other ones where you had e to the x. The derivative of e to the x is still e to the x. Well, so is the antiderivative of it. Would also be e to the x. But I've got a plus c. If I was to go from the antiderivative to the original, I do so by doing the derivative, and the derivative of e to the x is e to the x. The derivative of that is also e to the x. So you just basically just keep going in that circle. Okay, so if I have e to the 2x, okay, e to the 2x, so here I have the derivative of that would be 2e to the 2x. Bring your derivative of your exponent times e to the 2x. While doing the antiderivative of that, I'm still going to have e to the 2x, but now I need to divide by the derivative of that exponent. So we divided by, so we multiply by 1 over 2 plus c. So before I was multiplying by my exponent, now I'm going to be dividing by the derivative of that exponent. 1 over x. Okay? Now 1 over x, when you go to take the derivative of that, okay, you need to express your function as being in where you have it as an exponent, so x to the negative 1. And when you go do the derivative of that, it becomes negative 1x to the negative 2. Now when I go to integrate, though, 1 over x, that would have came from the natural log of x plus c. Now I put the x of the natural log in absolute values because you can only take the logarithm of a positive number. Okay? So 1 over x, the antiderivative of that, the integration of that is natural log absolute value of x. A few more. 1 over 3x plus 1. If I was to go and take the derivative of it, I would have to first express it as being f of x equals 3x plus 1 to the exponent of negative 1. And then I have to use the chain rule, negative 1, 3x plus 1, negative 2, multiplied by 3, can be simplified, negative 3, 3x plus 1 to the negative 2. I would have to use a chain rule to do that, and again, you can keep on going further, get rid of your negative exponent. However, if I want to do the antiderivative of it, the 1 over, what again came from the natural log. Natural log, absolute value, 3x plus 1. But now I need to divide by the derivative of the inside. So it'll be divided by 1 over 3. And then again, include my plus c. So anytime you had a function, and you want to do the antiderivative, and if the function was 1 over something, it probably came from the natural log. Sine. The derivative of sine is cos. Well, the antiderivative, what would it have been before to give you sine? It would have had to have been negative cos x, and then again plus c. Positive cos would give me a negative sine. The derivative of positive cos is negative sine, so the derivative of negative cos would have to be positive sine. And if I have a trig function, sine x or sine 3x plus 1, when you go do the derivative of a trig function, you have to take the derivative of your angle, multiply the derivative of your angle, cos, the angle stays the same. Well, when I go do my antiderivative, in this case it would be negative cos, angle always stays the same, but I have to be negative and I would have to divide by the derivative of the angle. Before I multiply by the derivative of the angle when I'm doing the derivative, now when I'm doing the antiderivative, I need to divide. So it would be negative 3 cos 3x plus 1 plus c. Then I have cos 4x. Okay, the derivative of cos is negative sine, so you had negative 4 sine 4x. Well, I'll do the antiderivative. What would give me cos? It would be a positive sign. The angle stays the same, still 4x. But I have to divide by, when I'm doing the antiderivative, I divide by the derivative of the angle. So 1/4 sine 4x plus c. Okay, so just some lesson, just a little lesson on different rules for integration. Thank you very much.